Hello class, Professor Anderson here. Let's talk about the E field of an infinite line of charge, and let's see how we can figure out exactly what that E field is. So first off, let's draw a coordinate system. Here is our XY coordinate system. And now we need to draw an infinite line of charge. So we'll make that infinite line right along the x-axis. Okay, and we'll make it orange. So this is an infinite line of charge. Even though I did not draw it infinitely long, just pretend that that charge keeps going out in either direction. And we're going to give that line a charge positive lambda. So what is lambda? Lambda is charge per unit length. Okay. And now we need to figure out what the E field is. And let's take a look at the E field up here at this point right there. And we'll say that that is a distance y above our charge, our line of charge. All right, so how do we do this? Well, when you're faced with any sort of problem that has infinity in it, you probably immediately think, well, that's impossible. So we need to break it down into some smaller chunks that we can manage. And that's exactly what we're going to do. Let's say that I take a little piece of this line right there. Okay? And that little piece of line has an amount of charge in it, positive Q. Now, positive Q charge means that electric field lines are coming out of it. So if I think about the electric field from that little chunk of charge up here at our point of interest, it's going to look like that. All well and good. But what about the idea that we have an equivalent charge right on the other side? So if I go over here, I can pick any mirror image of that thing, and that's also going to have positive Q, and that's going to make an electric field that's pointing in that direction. So if I take just those two pieces of charge, and now I look at the net field up here, what do I get? Well, the horizontal components are going to cancel. The vertical components are going to add. We'll make our axis a little bit longer there. And so we're going to get a net electric field that is going up. Okay. So by symmetry, we can argue that any electric field above this line has to be pointing radially outward from that line. But how do we calculate exactly what that is? All right, let's think about it for a second. If I have a little chunk of charge here, then I should really call that little bit of charge dq. Right? D is just like a little piece. But what is dq really? dq is charge per unit length times length. So dq is equal to lambda times some dx. If that little slice of charge is dx and that little slice is dx, then I get lambda times dx for both of those. We're out here a distance x away. We're up at a distance y. So let's see if we can calculate what the E net is for this configuration, and then we'll see how we can expand that to plus and minus infinity. All right, this gets a little tricky, so hang in there. Let's do this E field right here and figure out what the components of it are. So I'm going to take this one, I'm going to blow it up a little bit. It has a vertical component, E sub y, and it has a horizontal component, E sub x. We already said that we're not going to worry about the horizontal component because those are going to cancel out. It's really just that vertical component that we're worried about. Let's do one more thing here. Let's make this angle theta. And that angle is also, therefore, theta. All right. If that angle down there is theta, then this angle's theta. What about this angle right here? Is that one theta? No, it actually turns out that this one right there is theta. Okay, and you can convince yourself of that pretty quickly, right? Parallel line, bisector, parallel line means that one has to be theta. So let's not worry about this angle, but let's worry about this E sub y. What is E sub y now? Well, this is the right angle in our triangle. E sub y is therefore the hypotenuse of the triangle times sine of theta. All right, that looks pretty good. Now, if we can figure out what E is, we're probably going to be in good shape. But we know what E is. E is just the electric field from a point charge. All right, what is that? It is the charge, dq, divided by 4 pi epsilon naught r squared. And then we still have that sine theta hanging out there. All right, that looks pretty good. But what is r? R is this distance right here. And we don't know exactly what it is, but if we write it in terms of these other variables, it's not too bad, right? It's just x squared plus y squared. And then we're still hanging on to our sine theta. We're almost there, but it would be nice to write this sine theta in terms of some of these variables, and we can certainly do that because we have those sides of the triangle. What is sine theta? It is y over r, which is x squared plus y squared to the 1/2. All right, I told you it was a little complicated, right? X squared plus y squared to the 1, x squared plus y squared to the 1/2. It looks like we can write out this E sub y, okay? And to be technically correct, we're going to call this d E sub y. And it's going to be twice this value. Why? Because we have 1 from this pointing to the right, we have 1 from this pointing to the left. They both add up vertically. And so this becomes 2 times dq divided by 4 pi epsilon naught x squared plus y squared. And then we have a y, and this in the denominator became to the 3/2. Okay, that's what our dEy looks like. Now, how do we find the net electric field from all this stuff, from the complete line? Well, that is pretty tricky. The way you do it is you integrate both sides, right? If I want to find the net electric field up there, I have to integrate dEy over all the contributions here, which means I have to integrate this thing to dqy over 4 pi epsilon naught x squared plus y squared to the 3/2. But I don't really know how much total charge there is. Well, I do. I know it's a lot, right? So let's rewrite this dq as lambda dx. And let's see what we get. We get 2 lambda dx times y divided by 4 pi epsilon naught x squared plus y squared to the 3/2. And a lot of this stuff is in fact a constant, and so it can come out in front of the integral. What is a constant? 2 is a constant. Lambda is a constant. That would just be some given amount of charge per unit length. Y is in fact also a constant, right? We are at a fixed height above the line. 4 pi epsilon naught is a constant. And then we're left with the integral of dx over x squared plus y squared to the 3/2. Now, what do we have to integrate from? Well, remember this factor of 2? Okay, that factor of 2 came because we have a mirror image on either side of the origin. If I have a positive charge here, I have a positive charge over there. Okay, and so we said we didn't need to take twice the vertical component. So that's where that factor of 2 came from. Which means in our integral, we don't have to integrate from minus infinity to plus infinity. We have to integrate from 0 to infinity. We are just starting here and integrating out because we've already taken into account the other side through that factor of 2. All right, this is E at that position Y. And now you're faced with doing this integral. And that looks a little challenging, right? Try it yourself and see what you get. Cheers. All right, don't be mad at me. How do you do this integral? Well, you look it up in the book, in the appendix, or you can go to Wolfram Alpha and plug it in and he'll tell you the answer. I'll just tell you what the answer is. What is the electric field a distance y away from a line charge? It's the following. We still have that constant out there, 2 lambda y over 4 pi epsilon naught. This whole integral, in fact, simplifies to 1 over y squared. Remember, y is a constant. You're integrating over x. So look up how to do this integral. It works out to be 1 over y squared. And therefore, one of those y's cancels out, and we get the following. Lambda over 2 pi epsilon naught 1 over y. What's the electric field a distance y away from an infinite line charge? It's that right there. And it's sort of interesting that it falls off like 1 over y. Remember the point charges fell off like 1 over r squared? This thing falls off like 1 over r. What about a plane? As we're going to see, a plane, in fact, has a constant electric field above it. All right, that's it for now. Hopefully that's clear. Cheers.